Let us continue to study interaction picture method. We will construct interaction picture method and recompute we derive the Fermi's golden rule using this way. Until now, we have been using the Schrödinger picture in which expectation value of an operator is expressed in this way, where the state cat is dependent on time. It makes a time evolution, and operator in Schrödinger picture does not change. For example, kinetic energy p squared over m squared and potential energy was independent of time. So we assume in Schrödinger picture, operator is independent of time, and time evolution effect can be factorized as an operator exponential minus I over h bar Hamiltonian time acting on the state cat at time t equals 0, where the h has eigencats n whose eigenvalue, energy eigenvalue is En. If you take the complex conjugate, this becomes, because h is omission, I only have the sign difference, and the state cat, we have the expectation value of an operator at time t can be expressed as, if we pull out this wave cat at time t equals 0, we write the time evolution operator in the Schrödinger picture, and it's a complex conjugate, Hermitian dagger. Okay, let us define the wave cat in Heisenberg picture in which it is independent of time. Okay, in that case, the time evolution effect is acting on the operator. So this is the Heisenberg picture wave function, which is independent of time, and now dependence on the time is absorbed into the dependence of the operator. So this is the wave cat in the Heisenberg picture, and this is the operator in the Heisenberg picture. Actually, what we calculate is just expectation value of an operator, so that is exactly the same. Whether the viewpoint is that whether we include this time-dependent factor to the state or operator. That's the big difference. So in Heisenberg picture, the Schrödinger operator is transformed into this form. Okay? Again, operator's expectation value is the same. So this was the Schrödinger picture's state, and this is the Schrödinger picture's state at t equals 0. So if I want to obtain the Heisenberg picture, it is exactly the same as the Schrödinger picture, only at t equals 0. That means I have to kill the time evolution effect that appears in the state at t equals non-zero. Okay? That was this exponential with negative sign. In order to kill that effect, I multiply plus, right? Or where's the definition? Right. You know what I mean? Just if I multiply this, I have negative sign and I multiply positive sign to remove this. This is psi t of s, and this is again psi 0 s, and that is exactly the same as psi h, right? To kill this effect. Okay. So from what is that? Oh, right. From this in Schrödinger picture, state is evolving with negative sign, and what I have done is just to multiply positive sign, that is complex conjugate, that is inverse, to kill this effect. So interaction picture is similar to the Heisenberg picture, except that we remove the time evolution of the state due to the H0 only. Okay. The reason is that in the previous derivation of the Fermi-Golden rule, the contribution of H0 in the equation cancels in the left-hand side and right-hand side, and the effect of the potential survive only. So that is the reason why we want to remove the H0 effect. If we remove the H0 effect in the evolution, then what's happening is that it is effectively the same as canceling the left-hand side and right-hand side and the H0 piece in the Schrödinger equation. Remember? So interaction picture is exactly the same as Heisenberg picture, except that I replace this H by H0. Okay? So still the evolution of the state due to the potential survives. Okay. In reverse, if I want to compute the Schrödinger picture state from the interaction picture, what I have to do is just to multiply its complex conjugate. Let us write down the expectation value of an operator in the Schrödinger picture, and I replace the Schrödinger picture wave function using this one. So I substitute it here, and it's the complex conjugate is here. So I can define this guy to be the operator in the interaction picture. Okay. Alright. Let us go back to the Schrödinger equation, and this Schrödinger equation is written in the Schrödinger picture. I'd like to rewrite this one in the interaction picture. Let's see what happens. In the interaction picture, one question. If we rewrite the Schrödinger equation in the Heisenberg picture, what happens? Homer. So let us rewrite this guy by making use of the interaction picture. So what I have to do is just to replace this Schrödinger picture state by this equation, right? So substitute this interaction picture wave function multiplied by time evolution due to H0, right? So if I substitute in here, what I get is I have bracket, and this is Schrödinger picture state that is now exponential minus I over h bar h0t interaction picture wave cap. I used S in order to identify this potential is written in the Schrödinger picture, and here I substituted this Schrödinger picture state by expressed in terms of interaction picture state. Alright, we will see that this H0 disappears in the final stage. and actually in here. Alright, if I take the time derivative, we assume that h0 is independent of time. h0 is independent of time. In that case, if I take the derivative, what I get is h0 either to the left hand side or the right hand side, because this exponential is a polynomial of only a single operator, h0. h0 commutes with h0 nth power. So if I take the derivative, then I have minus I, so this over factor cancels, and either h0, this operator, or this operator times h0. So here I wrote h0 inside. And then this derivative can be acted on either this or that, right? So first term is written here. If this differentiation acts on the state, then I have this operator. Now the exponential factor is factored out. Here, I have h0 already, and h0 can commute, but let us leave it as it is. So h0 v of s, v sub s, and the same operator. Next step is, I don't like this factor. Let us multiply the inverse of this operator. That is simple, just to replace this one with the positive sign. Then this exponential factor disappears. Instead, I have positive power exponential plus I over h by h0 t appears in the left hand side of the right side. Finally, I have this exponential. Regarding this, I have h0 e to the minus I h0t plus I over h bar h0t, and this is just h0, right? Because they commute and they are inverse, and it is h0. So this is this. And next one is potential. I don't know whether potential commutes with h0 or not, so I leave it as it is. And as we have defined, operator multiplied by exponential plus I over h by h0 t operator, exponential minus I, blah blah blah, equals interaction picture operator. So now this can be written as interaction picture potential. Alright? And now this h0, and this h0 in both sides exactly cancel. And final result for the equation of motion in the interaction picture does not have h0 dependence at all. So this evolution of interaction picture state depends only on the interaction picture potential. And actually there's an h0 dependence appears. If they commute, then h0 dependence exactly cancels, but if they do not cancel, then we would have the energy dependence over a factor. You remember in the when you derive the transition amplitude, you have some frequency factor omega m and t, something like that. That guy appeared due to this. Let us find the time evolution operator ui t0. Then let us define. I'm interested in the state evolution in the interaction picture, and I'd like to know this operator. Then I can do any calculation at time t. For example, the expectation value of an operator at time t can be computed if once I know the initial state wave function. Right? So we'd like to solve this differential equation to find ui. Okay, that's it.